Afternoon session looking at applications where we have FPGAs working on linear algebra, but sometimes it's linear algebra with a twist and a special purpose. So what you're going to see is three presentations this afternoon. We have Junkyu Lee, who's a grad student at University of Tennessee, and he's working in this space, and when he gets done, he actually was looking for a research type position. So those of you out there, you've got a candidate in front of you. The second presentation will actually be by Mai Quing Wang. I don't know if I said that entirely correctly, but we hope it's close enough. And he is an assistant professor at the University of Arkansas who got his mentoring in this area from Tarek at the George Washington University. He's an assistant professor of computer science and computer engineering. So he'll be giving us a second presentation looking at applications with FPGAs and double precision floating point in the Hessenberg reduction. And the last presentation caught my eye out there because I was trying to question how you got to zero latency. And what we are going to have is a presentation by Craig Petrie, who is a product manager, and we clarified that the title is actually a little bit of marketing speak in there, but these are actually near zero latency types of matrix vector multiplication. So that's our panel or our presentations in this particular session. So we will just get started and take it away.
Hello everyone.
We're going to do a mic test.
Hello. Hello everyone. My name is Junkyu Lee, and I'm from University of Tennessee Advanced Computing Laboratory. My co-workers is Chun Chin Soon, Gregory D. Peterson, Robert Jerry Harrison, and Robert J. Hindi. We'd like to thank NSF to support this project, and I'm going to start with the topic of power or performance of this precision linear servers for FPGAs and GPUs. So in high-performance computation science applications, I guess everyone here is interested in using accelerators to accelerate computations because this conference is about accelerators such as GPUs and FPGAs. And power becomes a significant issue in such high-performance computation science applications because computation-intensive tasks requires huge power. So we realize that linear system server is one of the famous applications in computation science applications. So in mixed precision linear system servers, we can exploit precisions to optimize the performance. So we can choose precisions according to system matrix characteristic, such as condition number or matrix size. So we realize that it will be interesting to observe the power or performance for mixed precision servers, which GPUs and FPGAs according to system characteristics, such as matrix size and condition numbers. So before we investigating the power performance, I want to simply describe about the impact of manipulating with the precisions for computations. Most computing platforms.
I'm sorry. Put your microphone on your.
Okay, I guess it's.
Yeah.
Most computing platforms nowadays, most computing platform employ just single or double precisions. So there is limitation to exploit precisions to optimize performance. However, the FPGAs can employ arbitrary precisions, so we can fully exploit the precisions to optimize performance in such platforms. For such platform, which we can use arbitrary precisions, then we can play with the precision to optimize precision. So when you employ the low precision, there is a lot of benefits to obtain the high performance. Because if you employ the smaller ALUs, then which means then you can employ also the shorter wires and shorter pipeline in a single ALU. That means you can employ faster clock rate. And also number of arithmetic units in fixed area can be reduced. Number of arithmetic units in fixed area can be decreased because you employ the smaller arithmetic units. So you can expect the speed up. And also number of transistors in single ALU can be reduced. So you probably expect that building cost for a single ALU will be decreased. So based on these factors, then we can expect the speed up with playing with precisions in a computation. So I want to describe what is mixed precision solvers. So mixed precision solvers basically to employ multiple precisions for computations to optimize performance. So it employs low precisions for computation-intensive tasks, expecting high performance, and it employs higher precision for less computation-intensive tasks to refine the solutions. So based on this method, we can expect high performance. Also, we can expect higher accurate numeric solutions at the same time. This is mixed precision solver history. So first you have system equation, which is A is equals B, A is vector and B is A is matrix and B is vector. Because these are computers employs just steady and fine precision computations, such as single or double precisions. So the solution X is error-prone. To produce better numeric solutions, in 1948, James Wickens proposed iterative refinement to produce better numeric solutions in such system equations. In 2006, there is a new version of iterative refinement proposed to produce better numeric solutions and high performance at the same time. Okay, I want to describe how to solve system equations briefly. Suppose you have system equations such as A is equals B. The first step you have to do is you have to decompose matrix having two triangular matrices. You can also use this is called LU decompositions, but you can also use QR decompositions to solve system equations. But QR decomposition takes twice more time than LU decomposition. That's why LU decomposition is widely used for now to solve system equations. Once you obtain lower and upper triangular matrices using LU decompositions, then you can find out the intermediate solutions, which is represented by Y. Y represents U matrix times X here. So Y can be found out from top to bottom because of the shape of lower triangular matrix. So for example, if the Y0 can be found dividing B0 divided by the first element of lower triangular matrix. And once Y0 is found, then Y1 can be found easily using back substitution. So once you found out the intermediate solution Y, then you can finally find out the final solution X using upper triangular matrix. When in here, when you look at the shape of upper triangular matrix, X can be found from bottom to top. So I hope you notice that this matrix composition takes most time because it has n cube computational complexity. Others just has n square computational complexity. So we only employ lower precision for matrix decompositions, and we only employ high precision for less computational intensive tasks to produce better numeric solutions, expecting high performance by employing lower precision for computation intensive tasks. So this slide represents the mixed precision algorithm. Mixed precision algorithm consists of two steps. The first step is called approximation step. In approximation step, the algorithm will do LU decomposition and then find out the approximate solution X. Once you find out the approximate solution X, the approximate solution goes through the refinement step until it reaches numerically